Hello everyone and welcome to my channel Chemistry by Miss Nidhi Banga. Today's topic is reasoning or conceptual questions from the chapter Amines. So let's get started. Okay, so let's start with physical properties. Our first question is arrange the following in increasing order of solubility in water. So these are the compounds aniline, diethylamine and ethylamine. So the order that would be followed is this. Okay, ethylamine would be most soluble and aniline would be least soluble. Let's see why. So solubility depends upon hydrogen bonding with water. So this is our primary amine. Primary amine has partially negative nitrogen, partially positive hydrogens. Water has partially negative oxygen and partially positive hydrogen. So there is a possibility of hydrogen bond, and the extent of hydrogen bond is more in comparison to the extent of hydrogen bonding in secondary amines. Plus, in primary amines, there's only one hydrophobic group. There's only one hydrophobic group. So this repels water, but this is just one in case of primary amine. In case of secondary amine, there is lesser hydrogen bonding and there are two hydrophobic groups which are going to repel water. Okay, so obviously primary amine is going to be more soluble in water as compared to secondary amine. Talking about aryl amines, here the hydrophobic group is rather bulky. Is much bulkier than other aliphatic amines. So this is going to be least soluble in water. Moving on to the next question. Explain the boiling point order of these. So you have N-butylamine, diethylamine, ethyl dimethylamine. So this is also primary amine, secondary amine, tertiary amine. So here boiling point depends upon intermolecular forces. In case of primary amine, the intermolecular force between the amines would be hydrogen bonding. And hydrogen bonding we know is very, very strong. Okay, so we just saw in the previous question that primary amines, since they have two hydrogens bonded with them, there is greater chance of hydrogen bonding. Okay, but when we talk about secondary amine, because there is one hydrogen less, extent of hydrogen bonding would be less. In case of tertiary amine, there is no hydrogen. So hydrogen bonding won't be possible. The IMF here, the intermolecular force that would exist here would be dipole of this nitrogen-carbon bond. Okay, so interaction here would be dipole-dipole. Interaction here would be hydrogen bonding, but lesser in extent in comparison to primary amine. Talking about the next question, arrange the following in increasing order of their boiling point. So here we have tertiary amine, primary amine, and alcohol in comparison. So the order that would be followed would be this. Alcohol would have the highest boiling point and tertiary amine would have the least boiling point. Now, why is that? First, let's compare these two. Here, the hydrogen bonding is possible in both cases. The IMF, the intermolecular force, in both cases is hydrogen bonding. But hydrogen bonding in alcohol is much stronger than hydrogen bonding in amines. That is because in alcohol, the atom here is oxygen. Oxygen is more electronegative. Okay, so its interaction with the partially positive hydrogen of another alcohol molecule would be stronger. Okay, so since strength of hydrogen bonding is stronger here, this would have highest boiling point. Here IMF is still hydrogen bonding, but strength is less. Here there is no hydrogen bonding because there is no hydrogen to have a bond with, right? These hydrogens, they do not have partial positive charge because they are linked with carbon. Okay, so don't get confused. Okay, let us now discuss basic character of amines. Before we get to the questions, let's very quickly review about the basic character. Okay, so Kb is directly proportional to basic strength. Higher value of Kb would mean higher basic strength. But since pKb is negative log of Kb, higher pKb would mean lower Kb. or in other words, lower pKb would mean higher Kb, therefore higher basic strength. Now let's compare aliphatic and aromatic amines. Now aliphatic amines are more basic than aromatic amines. Why is that? Nitrogen has this lone pair. This lone pair is what grabs the proton from the acid. Okay, so this lone pair must be available for grabbing the proton, because basic character means what? Basic character is acceptance of proton, right? So in aliphatic amines, this lone pair is available to grab proton, whereas in case of aromatic amines, like aniline in this case, this lone pair is involved in resonance. Why? Because this lone pair is in conjugation with double bond in the benzene ring. So it's not really available to grab proton. That is why aromatic amines are less basic than aliphatic amines. Now, low basicity of aniline can also be explained in this way. Aniline, when grabs the proton, forms anilinium ion. Now, when product of a reaction is less stable than the reactant, the reaction is not likely to go forward. And anilinium ion is just that. It's less stable than aniline. Why is that? Because anilinium ion has only 2 resonating structures in comparison to 5 resonating structures of aniline. Let's see how. So these are the resonating structures of aniline. I hope by now you know how to make resonating structures. You can see that there are 5 of them. In case of anilinium ion, there are only 2 resonating structures. This actually doesn't get involved in resonance. Only the pi bonds are involved. Pi bonds in the benzene ring are involved in resonance, right? But why is that? You might feel that this bond can get here and a positive charge can get here, and then this bond can come here and positive charge can go there. That is not possible, because when this happens, if this were to happen, nitrogen would be making 5 bonds, and that is not possible because nitrogen has only 4 orbitals, 2s and 2p. Okay, it has only 4 orbitals available, so it can maximum form 4 bonds. So this won't be possible. Okay, that is why anilinium ion can form only 2 resonating structures. There are only 2 resonating structures in anilinium ion in comparison to 5 resonating structures of aniline. Moving on, when we compare about substituted anilines, there's a very simple formula. Formula is in the very simple trick. The thing is, if there is an electron donating group substituted with aniline, an electron donating group such as alkyl or OR, now they tend to increase the electron density on benzene ring, therefore increase the electron density on nitrogen, which would be used to grab the proton, therefore justifying the basic character, right? But if there is an electron withdrawing group attached, such as these groups, this would withdraw the electron density, making lone pair of electron on nitrogen even less available for donation. Therefore, when there is an electron withdrawing group with associated with aniline, the basic character would be less. Okay. Up next, comparing now the basicity amongst aliphatic amines, right? So tertiary aliphatic amine in gas phase is more basic than secondary, then primary, then ammonia. Why is that? So these are your molecules. Nitrogen's lone pair are used to grab the proton, therefore the basic character. Now here, these lone pairs are more available. Why? Because of the plus I effect of the 3 alkyl groups, right? Which is less in the secondary amine, even less in the primary amine, and none in ammonia. And that's not all. When the tertiary amine grabs the proton to form substituted ammonium ion, this nitrogen gets a positive charge, which is stabilized by the plus I effect of the R. Okay, now this is more stable than the substituted ammonium ion of the secondary amine, right? So simple answer is that in gas phase, this is the trend that is followed, tertiary greater than secondary greater than primary, and ammonia for the basic strength, simply because more alkyl groups, that means more plus I effect, that means the electron would be more available for donation. Moving on about the aqueous phase. Now, aqueous phase is not all that simple. It has two effects. Plus I effect, which we just discussed, which makes tertiary amine more basic than secondary than primary. But then there is a solvation effect, which acts in the opposite direction. Basically, which makes primary amine more stable than secondary than tertiary. Primary amine more basic than secondary than tertiary. Why is that? And what is the solvation effect? So, upon grabbing the proton, this is the substituted ammonium ion. Now, this is primary substituted ammonium ion, this is secondary substituted ammonium ion, and this is tertiary substituted ammonium ion. When we talk about aqueous phase, definitely there is going to be water. Now, water would be able to stabilize these substituted ammonium ion by hydrogen bonding, which is more so in primary, less in secondary, and least in tertiary. Okay, so solvation effect means the stabilization of substituted ammonium ion, that is the product. Okay, stabilization of substituted ammonium ion by solvation, which would happen more in primary than secondary than tertiary. So these are the two effects in play and they are in opposite direction. So what would be the net result? The net result is this. Obviously, secondary is going to be most basic, okay? But then if you have an alkyl group, a small group, primary would be more basic than tertiary. But if you have an ethyl group, a bigger group, tertiary would be more than primary. So easiest thing is just remember for one, just remember this number 213 is for methyl. Because methyl is small, a smaller number comes first than the bigger number. Okay, just remember this and the opposite would follow here. Okay, now let's practice some questions. First, amines are more basic than alcohols. Why? So this is your amine, this is your alcohol. The difference is oxygen in alcohol is more electronegative than nitrogen in amines. So that means oxygen is holding on to these lone pair of electron very tightly, not willing to lose them for grabbing the proton, right? Not willing to donate these. Whereas nitrogen, being less electronegative, is okay with donating the lone pairs. And that's not all. After grabbing the proton, it forms this substituted ammonium ion, and here this is the product. Now what happens is, here there is positive charge on less electronegative nitrogen. Here there is a positive charge on more electronegative oxygen. So this is not a happy situation. This is less stable because positive charge on more electronegative atom is making it less stable. So the product here is also less stable than the product here. Okay, that is why amines are more basic than alcohols. Moving on, amines are basic while amides are neutral. Why? Amines can donate their electrons to grab proton, whereas amide are unable to do so because here the lone pair is in conjugation with double bond. So it's involved in resonance. Moving on, arrange in the increasing order of their basic strength. Okay, so this is the order. Why? Because here we have primary amine, which is basic. Aliphatic amine, we know that aliphatic amine is more basic than aromatic amines. So this is obviously most basic. Now, comparing these three. So these are the structures. Here we have, this is least basic because we have two benzene ring with which the lone pair of electron can get involved with in resonance, right? Here we have only one benzene ring. Okay, so this is least basic. Here lone pair is not at all available. It's very busy by getting delocalized over the benzene rings, over two benzene rings. Here there's only one benzene ring, so it's comparatively more available. Now here there is benzene ring, yes, but then there are also two alkyl groups which by plus I effect are increasing the electron density on nitrogen, therefore making it more basic than this. Okay. Okay, same question, arrange in increasing order of their basic strength but different molecules. So the order is this. Now secondary amine, secondary aliphatic amine obviously is more basic because of the two alkyl groups. So twice as much plus I effect. Here there's only one alkyl group. Here there is, now here this is aniline and this is benzylamine. Now, in case of benzylamine, the lone pair of electron are not involved in resonance because they are not in conjugation with double bond. So they would be actually more available than this. Okay, but it's still less basic than aliphatic amines because there's no plus I effect, not as much. Okay, here there is involvement of lone pair with benzene ring, therefore it would be least basic. Moving on, same question, different molecules. Now this time we have all aromatic amines and the order is this. This is para-nitroaniline, aniline, para-toluidine and NN-dimethyl para-toluidine. Okay, this is least basic because apart from the lone pair being busy, there is an electron withdrawing group which is pulling the electron density. This is lone pair being busy here. Here, lone pair is busy in resonance, but then there is an electron donating group which would increase the electron density on nitrogen. Here, we have that plus two additional alkyl group directly in contact with nitrogen, which is increasing the electron density on nitrogen even more so. Okay, so that is why this is the trend. Next question. Why using scrap iron and HCl is a preferred method to reduce nitro compounds? So this is your nitrobenzene and we are using iron scrap and HCl to form aniline. First thing is that this iron is iron scrap, so it's cheaply available. Okay, it's cheap, so we can get easy access to that. Then next is that when it reacts with HCl, it forms FeCl2 and H2. This hydrogen is actually carrying out the reduction and the FeCl2 that is formed gets hydrolyzed to form ferrous hydroxide and HCl is released. So this HCl is regenerated. So in the beginning, we'll have to add a little HCl, but after that, the reaction takes care of it. Okay, that is why this is preferred method. This is economically viable method. Moving on, why ammonolysis of alkyl halide is not a preferred method to produce primary amines. So this is ammonia, this is a nucleophile. Alkyl halides undergo nucleophilic substitution. So these electrons would attack the partially positive carbon here and will form primary amine. But the primary amine can also act as a nucleophile and can attack RX again, leading to formation of secondary amine, which would again act as a nucleophile and lead to the formation of tertiary amine and then quaternary amine. Basically, it would yield a mixture of products. Okay, so we will not have pure primary amines. Next question, why Gabriel thalamide synthesis is preferred for synthesizing primary amines? So this is your Gabriel thalamide synthesis. It's preferred because, like we saw in the last method of preparation, ammonolysis, that ammonolysis gave mixture of products, mixture of primary, secondary and tertiary amines. The advantage of this method is that it gives you pure primary amine. Okay, moving on. Next question from the same topic. Why primary aromatic amines cannot be synthesized by Gabriel thalamide synthesis? So in Gabriel thalamide synthesis, this thalamide acts as a nucleophile and attacks on RX to form RNH2 by nucleophilic substitution. So if you want to make aniline or aromatic amine, your R here should be benzene ring or aryl halides, and we know that aryl halides do not undergo nucleophilic substitution. Next question. Tertiary amines do not undergo acylation reaction. Why? So this acylation reaction of amines can be considered as replacement of hydrogen with acyl group to give amide, right? Now tertiary amines do not undergo this acylation reaction because tertiary amines do not have replaceable hydrogen. So for the reason of absence of replaceable hydrogen, tertiary amines do not undergo acylation reaction. Moving on. What is the role of pyridine in acylation reaction of amines? So this acylation reaction takes place in presence of a base stronger than amines, that is pyridine here, to give amide and HCl, right? Now the use of pyridine here is that we can see that there is acid generation here. So this pyridine being a base can combine with the acid to form pyridinium chloride, a salt which can be precipitated, therefore can be removed from the reaction mixture. When it can be removed from the reaction mixture, it would shift the equilibrium to the right. Okay, to make more of this HCl by Le-Chatelier principle, the equilibrium would be shifted to the right. Acylation or acetylation of aniline reduces its activation effect. Justify. So this is aniline. Here the lone pair is in conjugation with double bond in benzene ring. So they get delocalized over the benzene ring. Therefore they increase the electron density of benzene ring. Therefore activating it, that means electrophile would be very, very attracted to benzene ring. Okay. So it makes it activating and ortho-para directing. Okay. But now the problem is that when the electrophile attacks on aniline, we get polysubstituted product because this benzene ring is very, very activated. So we get ortho product and para product all at once, right? So we get 2, 4, 6 substituted aniline. But what if we wanted to make only para substituted aniline? In that case, acetylation works. When we treat aniline with acetyl chloride or acetic anhydride, we get acetinolide. Now this acetinolide, in this acetinolide, the lone pairs are involved in resonance with the carbonyl group. So they are not as much available for resonance or for delocalization over benzene ring. Therefore, the electron density on the benzene ring is not as increased, okay, as in aniline. So the activity is reduced, and since there's a bulky group present here, we won't even get ortho products. We will get only para product. Which reagent can be used to separate primary, secondary, and tertiary amines? The short answer is benzene sulfonyl chloride. I'm not writing the whole equation here, but know just this, that primary amines, when react with benzene sulfonyl chloride, they form a product which is soluble in alkali because the product has a very acidic proton. So because of the acidic proton, it gets solubilized in alkali. When tertiary amine reacts with benzene sulfonyl chloride, the product that is formed does not have the acidic proton. Therefore, it does not get that would be insoluble in alkali. Okay, so the precipitation formed would be insoluble in alkali. Tertiary amine, because of the absence of hydrogen atom here, does not even react with benzene sulfonyl chloride. So the reaction does not take place. So how do we use that knowledge to separate primary, secondary, and tertiary amines? So if we have a mix of that, we treat it with benzene sulfonyl chloride, and we know that tertiary amine would not react with it, so would remain in the solution, but primary and secondary amines would react and will form precipitates of primary and secondary sulfonamide. Now these precipitate would be mixed together, but we at least separated the tertiary. Now the residue contains primary and secondary sulfonamide, and we know that primary sulfonamide is soluble in alkali. So now we treat this residue with aqueous KOH, which would dissolve the primary sulfonamide, and therefore it would appear in the filtrate, and the secondary sulfonamide would remain insoluble, so therefore it would appear in the residue. Next question. Methylamine in aqueous medium gives reddish brown PPT of ferric chloride. Why? So methylamine is a base. When combined with water, it acts as a base and water acts as an acid. So it grabs the proton from water and generates OH ions. Now these OH ions combine with the ferric ions in the solution and form ferric hydroxide, which forms the reddish brown PPT. Next question. Although amino group is ortho and para directing in aromatic electrophilic substitution reactions, aniline on nitration gives a substantial amount of para-nitroaniline. So what happens is, aniline, when treated with nitrating mixture has acid. It gets protonated and forms anilinium ion. This anilinium ion is meta-directing. That is why you get a substantial amount of meta-nitroaniline. Next question. Why aniline does not undergo Friedel-Crafts reaction? So this is your aniline, and Friedel-Crafts reactions use anhydrous AlCl3 as catalyst, which is also a Lewis acid. Now, since this is acid and this is base, acid-base reaction takes place and it forms a salt. Now, this reaction consumes the catalyst which was meant for Friedel-Crafts reaction. And that's not all. It gets a positive charge on nitrogen. Now this positive charge deactivates the benzene ring towards electrophilic substitution. Okay. Last question for the day. Diazonium salt of aromatic amines are more stable than those of aliphatic amines. That happens because of resonance in diazonium salts, aromatic diazonium salts. right? This resonance you'll have to practice. So I hope this video helped, and if it did, please like, share and subscribe, and thanks for watching.